Hello. In this lecture I am going to discuss how to calculate pH of a polybasic acid. First of all, what is polybasic acid? Any molecule or any compound, if it provides more than one H plus ion, okay, through ionization, we call those compounds as polybasic acids. Okay, for example, H2S is a polybasic acid. H3PO4 is a polybasic acid. Right? We have actually we have plenty of examples. H2SO4 is a polybasic acid. Okay, so we have many examples. Now we need to find the pH of the polybasic acids. Okay, and here let me take so these are all polybasic acids. Examples of these are the examples. We have a lot of examples actually. Examples of polybasic acids. Okay. Now, suppose I'll take a general formula for a polybasic acid like HNA, where N is the number of hydrogen, replaceable hydrogen present in the molecule. Okay. Now what I'm going to do, I'll take 1 mole of this compound and I'll dissolve in some amount of water, in some volume of water. Okay, I'll put 1 mole of this compound, 1 mole, right, dissolve in some volume of water, so I'll get a solution. Suppose, assume that this molecule remains undissociated in the solution. If it remains undissociated, then the concentration of the acid is represented as C. Okay, let it be C. C is the concentration of the undissociated acid. Okay, it's an assumption, right? Assume that the molecules are undissociated. If it remains as such, okay, then the concentration of the acid should be C. But we know very well this molecule will undergo ionization. Okay, so first this molecule undergo ionization and it will release one H plus ion, and you'll get Hn minus 1 A minus ion. Okay, and here this is aqueous. I'm talking about aqueous solutions only. Okay, I'm not going to discuss other solvents. So in aqueous solution, how the polybasic acid dissociate? So it provides one H plus and form an anion. Okay, let the equilibrium constant for this step, for this equilibrium step, let it be Ka1. Okay, since it provides H plus, this should be an acid. For acid, we write the equilibrium, the ionization constant as Ka1. Ka1 is the ionization constant for the first step. Then this anion will undergo further ionization, Hn minus 1 A minus ion. Okay, it will donate one more H plus, it will donate another H plus and form Hn minus 2 A minus 2 ion. Okay, for this step let the ionization constant be Ka2. Like this anion Hn minus 2 A2 minus ion will release or will donate another H plus, okay, and form Hn minus 3 A minus 3 ion. For this step let the ionization constant be Ka3. Like this, depending upon number of ionizable hydrogen present, okay, you'll get many steps. Suppose if you have 3 ionizable hydrogen, then you'll get 3 steps, right? It depends upon how many ionizable hydrogens or replaceable hydrogens are present in the molecule. Okay, now all are in aqueous medium. Now see, we get H plus in the first step, we get H plus in the second step, we get H plus in the third step. So we have to find the total H plus ion concentration. Okay, so what is the total H plus ion concentration? Total H plus ion concentration is equal to H plus ion concentration from the step 1, then H plus ion concentration in step 2, from step 2, plus etc. etc. Okay, but it was found in most of the cases that it was found that the ionization constant for the first step is extremely high compared to the other ionization constants. Okay, so what I'm trying to say is that the first ionization, ionization constant for the first step, this is extremely high compared to the ionization constant for the second one. Okay, that means the ionization constant for the second step is very low, negligibly low. Then if you go to the next one, yes, it is still very low, right? Like that it goes. So keep this in mind. The first step undergoes maximum extent of ionization. So almost all H plus ions, or almost the H plus ion present in the solution is almost due to the first step only. The second step and third step, they are all other steps, they have very low ionization constant. That means the extent of dissociation is very small, negligibly small. Okay, therefore I can say that the total H plus ion concentration, okay, in the solution is approximately equal to the H plus ion from step 1 alone. Okay, you need not worry about the other steps, because the ionization constants for other steps are extremely low, right? Therefore pH can be given as therefore for the first step we need to, it is enough to find the H plus ion concentration from first step. Okay, and you know very well H plus ion concentration, right, for the step 1 is equal to degree of dissociation for that step. Let me write this as alpha 1 into concentration of the acid. This we know already, because in most cases, okay, the polybasic acids are weak acids. We have an exception, sulfuric acid is an exception, but in most cases polybasic acids are in general weak acids. Therefore you can find the H plus ion concentration using the weak acid formula. Alpha 1 is the degree of dissociation for the first step into C. Okay, and under the assumption, under the approximation, right, under the approximation that if square root of Ka by C, okay, or we know very well Ka is equal to, Ka1 is equal to alpha square C by 1 minus alpha. You know this formula. If alpha is very small compared to 0.05, okay, equal to or less than 0.05, then I can neglect this alpha compared to 1. So I can write Ka1 equal to alpha, let me write alpha 1 here, alpha 1 square into C. Okay, here alpha 1 is very small, so I am neglecting alpha 1, right? Then what is alpha 1? Alpha 1 equal to root of Ka1 by C. Substitute this value here, so we'll get the H plus ion concentration, right? Total H plus ion concentration. I'll call this as total H plus. Why? Because total H plus is nothing but H plus from step 1, right? Almost 99% of H plus ion is obtained from obtained through step 1 only. Okay, now so if I put alpha in the place of alpha 1, if I put this one, I'll get root of Ka1 into C after simplification. Therefore I can write pH as, so what's the pH? pH equal to, right, 1 by 2 into pKa1 minus log base 10 C. Okay, yeah, this is the formula we use to calculate pH of a polybasic acid. Okay, if you want to calculate pH of a polybasic acid, then this is the root. Okay, we consider only the first step. Okay, say for example, if we take say H2S, hydrogen sulfide, H2S in aqueous medium will undergo partial ionization and gives H plus ion in aqueous medium plus HS minus ion in aqueous medium. For this step, let the ionization constant be Ka1. Okay, and this will be around 10 power minus 4 or 5 like that. Okay, but if you take the second step, this HS minus ion will undergo further ionization and gives H plus and S2 minus. But the ionization constant for this will be very low. Okay, it will be in the order of 10 power minus 13. So if we compare Ka1 and Ka2, right? Yes, Ka2 is extremely low. Alright, ionization constant low means the dissociation is very low. That's the meaning. If dissociation is very low, then H plus from step 2 is very low, negligibly low. Therefore, you can consider H plus from step 1 alone. Right? So concentration of H plus, total concentration of H plus in this case is equal to H plus from step 1. Okay, or I can write directly that pH of the solution, right, under the assumption that alpha 1 is negligible. Okay, negligibly small, we can write pH equal to 1/2 into pKa minus log base 10 C, right, where I'll put Ka1 here. Okay, so you consider only the first step ionization constant. Okay, and calculate the pKa1 value, find the log C, subtract it and divide the value by 2, you'll get the pH of the solution. Okay, now here sulfuric acid is an exception. I'll write here H2SO4, it is a polybasic acid, but H2SO4 is an exception. Why it is an exception? The reason is, see, first step of sulfuric acid, the first step, it is it will behave like a strong acid. Okay, it is a strong acid, right? It will undergo complete ionization and gives HSO4 minus ion. For this step, right, alpha is roughly or approximately equal to 1. Alpha is 1. That means the first step will undergo complete ionization, almost complete ionization. So you will get huge number of H plus ions through first step. Then if you see the second step, HSO4 minus ion, this will undergo partial ionization and gives H plus and SO4 2 minus. For this step, the ionization constant, let me write it as Ka2. The ionization constant for this step, okay, it is very high. It is not negligible. Okay, it is considerably high value. Okay, considerably high value. What is meant by that? You cannot neglect this value. This is roughly in the order of 10 power minus 2. Okay, so depending upon the percentage of the sulfuric acid, okay, complete ionization may occur. That's why for sulfuric acid, often we write like this: H2SO4 undergo complete ionization, gives 2H plus and SO4 2 minus. Yes, this is well and good for almost all the cases, right? Only in few cases, right, depending upon the concentration of the sulfuric acid given, okay, only in few cases we'll consider this ionization constant, second step ionization constant. Okay, so in the numerical problem, very specifically, if this data is given, then you can make use of this data and you can calculate H plus from first step and H plus from second step, and you can add, right? Otherwise in general, if sulfuric acid is given, okay, you can consider that the H2SO4 undergo complete ionization and provide 2 H plus ion and the SO4 2 minus ion like this. Okay, you need not worry about the second step at all. Okay, so keep this in mind. This is very, very important. Right, for sulfuric acid, you treat sulfuric acid as simple strong, okay, like other strong acids. Right, only if this data is provided in the examination, numerical problems, then only you have to consider H plus from step 1 and H plus from step 2. Otherwise, you need not worry about that. Okay, good. So this is the information on the calculation of pH of a polybasic acid. Okay, yeah, I stop here. In the next class, I'm going to actually we have to discuss pH of a mixture of weak acid and strong base, weak base and strong acid, but this involves salt formation. Okay, the salt will undergo hydrolysis, right? So what I'm going to do, I will discuss salt hydrolysis first. Okay, once I finish those things, then I'll come back to the pH of a mixture of weak acid and strong base, and weak base and strong acids and all. Okay, yeah, I stop here. We'll continue in the next class.